Okay, and we go live. Hello, everyone, and welcome to another Sussex Vision Talk. As usual, I would like to remind you that these talks are part of the Worldwide Neuro Initiative. It's a global platform created already 1 year ago, and it has allowed us to continue exchanging our work and ideas during the pandemic. There are many live talks and podcasts on various topics, so just take the time to go on the website, check the different talks. I'm pretty sure you will find something of interest for you. Today, we would like to offer you something a bit different than usual, and something that will not only solely cover vision research. Today, instead of presenting data or sharing our newest results, we would like to engage our audience with a topic that we hold dear. It's a topic that we consider necessary for the good development of research and science in general. It's a topic which is known by many, but still underappreciated. So if you click on this video to join us, you know that today we're going to talk about open source hardware. And to do so, I am very glad today to receive my friend and colleague, Maia Chagas. So Andre studied biology at the University of Sao Paulo in Brazil. He then moved to Germany, where he obtained his neuroscience master and then more recently his PhD, which combined neuroscience and open source hardware. It was mostly based on open source hardware, let's be honest. For years, he's been volunteering at Trend in Africa, an NGO charity which supports scientific capacity building across Africa, where he operates as an open science coordinator. He is now a research bioengineer at the University of Sussex, where he provides support to research labs in the neuroscience department by developing various research equipment. Also, on his spare time, he offers consultancy services around open science hardware through the platform Prometheus Science. He's also an editor at PLOS for the open source toolkit. And to finish, he started Open Neuroscience, a network of collaborators trying to keep track and create interesting open source projects relating to neurosciences. And this we're going to discuss a little bit later. So, hello, Andre, how are you doing? And first question, where do you find the time to sleep?
Hi, Max. Hi, everyone. First of all, thanks for making the time and the space for me to talk about something that, as you mentioned, I hold quite dear, which is open source tools and open source hardware for research. I guess sleeping is, for everybody, overrated.
Yeah.
And I mean, all of these, like I started and I work on, but these are all collaborative efforts, right? So it's not just me, but a bunch of wonderful people all around the world who are actually pushing these agendas forward, right?
All right. So let's start. So Andre, we keep hearing about open source, open access, open science, etc.
Mm-hmm.
Can you give us a definition? Can you describe us what is open source? And in our case, what is open source hardware?
Yeah, absolutely. So open source, there is a very formal definition for it. It started with software back in the 60s. But how I like to describe it, that it's easy to understand, is basically something that we've always been doing, right? So you can think about this when you, let's say you cook a certain recipe, and you write down like what you cooked, and you have your recipe book and so on, and you want to share this with others, right? As you share the steps to make a recipe, a cooking recipe, and you're sharing this in a way that you tell people you can do whatever you want with this. You can cook it yourself, you can give it to another friend, you can actually bake cakes and sell, or you can make this recipe and sell it for a little bit of money. You can alter the recipe. This is basically open source, right? So open source is this idea of take the blueprint of something. It could be code, it could be equipment, it could be a cooking recipe, and share it with others using the certain guidelines that, like you showed the screen. And then, of course, hardware has its specific guidelines and software has its specific guidelines and so on. But the point is, we share and exchange knowledge by sharing the ways we've done things. Yeah, I think this is my definition of open source.
So it's technically an exchange of resources and knowledge about a particular topic.
Yeah, and exactly, right? And if you think about academia, this is super fitting to academia, right? Because we have like all of these public funded institutions and all of this money that's poured in from taxpayers' money, and we should basically freely share this back to the public because they paid for this in the first place anyways, right? And there were a lot of there is a lot of proof that sharing things freely in this way, be open access or be open source, actually speeds up the pace of innovation and increases the replicability of science and makes things actually better.
Yeah, okay. That I fully agree with. But here we're mostly talking about open science, let's say.
Mhm.
In our case, why should we care as scientists, as a researcher about open source hardware?
Mhm.
Why should we put such an interest and investment onto it?
So, I mean, there are a lot of reasons why, and a couple of them are basically makes you a better researcher in the sense that if you understand your tools, if I have something that it's open source, I can read the design files, I can learn everything in there, how it works to minimal details, right? And if I know this, I know exactly what my machines are able to do because nowadays it's impossible to do science without equipment. And so if I know what they're able to do, I know exactly what kind of data is coming out of them, and I know if they're out of calibration. I know if they're not behaving the way they should, right? And so this is the first thing. So you can nicely know when your devices are properly working. This is one. But then two is if I know exactly how something works and I have a different question that I want to ask, I can easily change this device to actually make it record the data that I needed to record for my new question. So in a way, you as a researcher, you become able to ask questions and adjust your equipment around it, and not the other way around where we have nowadays, where oh, I have this two photo microscope that is only able to do, let's say, 4 hertz per as a recording speed, right? And so if I have an open source version of my microscope and I can actually change the frame rate or put faster Galvo mirrors or something like that, I can actually then say, okay, I can now record from these cows, like these new indicators that are faster, except of being stuck with my 4 hertz black box to photo microscope that I bought off a company that doesn't share with me the inner workings and the design files.
Yeah, but in your example, you're taking something which is high tech, which is something
Mm,
very specific that not everybody will be able to access.
right.
Will you have an example of, I don't know, some things that in common lab you will be limited by and
Mhm.
you should invest time in as a reproduce or develop?
Absolutely. So we have, I think, two very good examples of something, of two things that are used a lot in research labs, and they're namely, so one, micropipettes. And as we know, these needs micropipettes are super used in cell biology, in molecular biology. And recently, as you're showing, there is a paper that describes an open source hardware model of a pipette that actually fits or complies with accuracy standards, with ISO accuracy standards. So basically, what this says is that this pipette that has syringes and 3D printed parts is basically able to perform as well as the commercially available ones within this ISO standard.
Yeah,
And
but
so the nice thing about this, which the benefit that this brings is, as I mentioned, you could in principle calibrate this pipette every day before you start your daily routine in the lab, which is not something people do when they have a commercially available one, because either they don't have access to a calibration service, or it's too expensive, or they don't have the time because the pipettes need to go out, be calibrated, and come back, and then they lose time with this move back and forth of the pipettes. And so this already by itself is a good thing because they are like orders of magnitude cheaper than commercially available ones, and you could build many of them. So, for instance, if you think about education, you could have, together with other tools that we're going to talk about, you could have a molecular biology lab for education where each group of students get a small kit and they're actually able to do the experiments and amplify DNA and actually do all the normal steps inside a molecular biology lab or a neuroscience lab.
so you think that if we invest into open source hardware, for example,
Mhm,
basic devices that just reproduce what we have in our labs, like a pipette, for example,
mhm.
that's something very common but very expensive and ever more expensive to maintain over time. If we have the capacity to produce them, to reproduce them and calibrate them ourselves, we can bring those kind of tools earlier in a biological education, so we can go further with our
Mhm.
education and our
Absolutely. Yeah.
research.
So, I mean, we gave the example of the pipette, and then a lot of people are going to say, oh, pipettes are not that expensive from the point of view of a research lab. But then I can give you another example, which are microscopes. So if you take a fluorescent microscope, it costs you at least $5,000 to $10,000 to set up a fluorescence microscope. And so, of course, you wouldn't put this in a bachelor classroom and tell 60 students at a time to go and have a crack at the fluorescent microscopes. What we have in the literature are several open source microscopes that actually can do fluorescence for under $100, right? And so you could actually build these microscopes and have 10 of them and still be saving money as compared to a commercially available microscope, which means, again, education, yes, and then you can have all these people testing and doing experiments even in a classroom in high school. But also, and this plugs to another point of open source hardware, you can have a massive parallelization of experiments, right? So if I have only one fluorescent microscope and 10 people in the lab, I'm going to have this booking system where somebody's going to end up coming late evenings, the weekends, and so on. If I have 10 fluorescent microscopes, on the other hand, then basically each person in the lab can have their own and do experiments in their own time. Or you could think about experiments that require much more data and you just have them running in parallel.
You can have redundancy in your data to support more accurate.
Exactly, and you can even replicate experiments much easier. And so this goes, again, in line with the philosophy of science that for something to be true, it needs to be replicable. You need to get the same results over and over again. Doesn't matter where you are, right? So this also increases how you can make your data trustworthy in a way. So it's not like a one-off, oh, I found this and maybe it's an artifact, but because it's so time consuming to reproduce this, we just have to take it for granted the way it is.
I mean, I fully agree with that. Once again, I consider that open science and open access replicability of data should be more common. But in our case, I mean, let's say I have a lab, why should I bother, let's say, investing time into developing or into reproducing such devices? Do you have, I don't know, for example, here in the Department of Sussex, you recently fixed a perfusion pump.
Yeah.
It was a silly example.
Yeah, so this is actually a very funny example, and I've been talking about this for a while now because it really still boggles my mind. So we have this little perfusion pump, yeah, that one that is being shown, and this thing broke in the lab. And although it's a simple piece of equipment, it's a vital piece of equipment inside a two-photo microscope, because this basically removes solution that is perfusing a certain biological tissue. Without this, the whole experiment and the whole microscope is stopped because you cannot remove the solutions and you cannot perfuse your tissue. And so this thing broke, and it took me basically, you're seeing here a quote for getting a new one. And it took me 2 days and 3 emails to get this quote. And this already kind of upsets me because this is not online, and everything in the world is the prices are online except for scientific equipment. We're not going to go into the discussion of scientific companies' business models, but this is already a little bit irritating and wasting my time. And so the other thing is these 2 days, and now as you can see, the lead times to get this was, for this pump specifically, was about 12 weeks. So if I would be only relying on this company to send me this, and the company is actually not an international company, it's here, actually very close by Sussex. It would take me 12 weeks with a microscope without being able to do experiments. And if you consider that a PhD project is about 3 years, this is a significant amount of time for being stopped. And here we're only considering the good case that this only broke once, right?
And talking about a silly device that you just
exactly. And then because my position here is about fixing devices and getting them up and running and producing new ones, I said, you know what, let me take a look at this closely. So I bring this thing upside down. And as you can see, I mean, you cannot see on this image, but as you come closer to the little black box, which is the pump, I hope you can read where it says aquarium equipment, which is now highlighted. And so basically what this company did was they put an aquarium pump in a very nice casing with these plexiglass sheets, right? Put some tubings, an Erlenmeyer, a pressure gauge, and now they're charging me 750 pounds for this with 12 weeks lead time. this must be said that this was way before the pandemic started, right? So it's not about like the pandemic is making this slower or anything. Like this is when best case scenario the world is working properly. And so what I did was, you know what, if this is an aquarium pump, I'm pretty sure I can find something online to replace it. And this is what I did. And this is what you can see here, how much it costs for an aquarium pump to do the same job out of eBay, buy today, get it tomorrow, if you pay a little bit extra for shipping. And so this is why we should care, or this is one of the reasons why we should care about how our tools are working, where we're getting them from, how is the supply chain working, and so on.
Yeah, that's a silly example. I mean, I'm outraged by that, but see here, for example, that's an hacker way you're describing. You're just describing a do-it-yourself practice when you're not afraid of taking the seal out of the box and see what's inside. And if you can consider why do they have a pressure gauge for that, I mean, that doesn't make sense. But it's not really the open source philosophy you talked about earlier. Do you have something which is maybe a little more state of the art or something which is more reliable in a lab?
Yeah, absolutely. So, and this is not work from me, which must be said. There is a device that was built in Tom Baden's laboratory in collaboration with a lab in South Africa, which is called Open Spritzer. And this is basically a device that delivers little air puffs. And the air puffs are really so tiny that you can put them in a tube. And if the other end of your tube, you have a capillary with liquid, you can deliver picoliter injections. And so this is used all the time to inject intracellularly solutions into cells. And so here you can see the repository where this is described and all the steps needed to build one of these are stored. And also the data, this was published as a paper, but then on the repository, you also put figures from the paper. And it's showing how it performs against the market known brand, which is a Pico Spritzer. And what they show in this paper is that it performs as well or even better sometimes than a Pico Spritzer. And so this is a little bit more high tech, so to say. But it's again showing that you can be much faster with development of experiments and much more affordable, which means you can have several of these open spritzers in place of just having one Pico Spritzer. So you could have in all your rigs, you could have one as a default.
Yeah, okay, so Pico Spritzer is about 25,000, 3,000.
3,000 to 2,500, you mean?
That's what I meant, sorry.
And so, and I think, if I remember correctly, the open spritzer is about 350 pounds or something like this.
Yeah, something like that, yeah.
So it's, again, like an order of magnitude cheaper than the other one.
Okay.
Right? And, yeah?
Oh, sorry, keep going.
No, I was going to say, and this is just one example. Another example, which is, and again, like here we're still in the realm of reproducing things that are already existing. If we think about what I mentioned before, design your experiments, and then think about making the tools, we have this other stimulator that, and this is totally fitting to the Vision series. We recently, this was already 2019, we published in collaboration with Thomas Euler's lab in Germany, the Open Visual Stimulator. And this is a projector. It's similar to a regular projector that you could buy from Amazon. And what is different is that we made it in a way that you can actually put pretty much any type of LEDs in it. And what you're seeing here in pictures is a system, like, can you stop there? Yeah, please. What you're seeing here is basically the system where we have two projectors working together at the same time, which allows us, here it's only depicted 4 LEDs. So for zebrafish specifically, where you have RGB and UV, but you could do up to 6 different LEDs. So basically you have a multispectral spatial stimulator that can do up to independently 6 different LEDs. And what needs to be said here is that this is a new thing. So there weren't any, as far as I know, there weren't any spatial stimulators that were able to take any type of LEDs and easily make them match the spectral distribution of cones in a specific species. So you have a lot of dedicated spatial stimulators for primates, but if you compare them to zebrafish, they have 3 cones, while zebrafish have 4 different types, and they don't have UV, And so if you use a primate stimulator to do zebrafish research, you are coming short in terms of what types of questions you can do, how well you're stimulating the organism that you're trying to study, and so on. So this is another point for open hardware in terms of that we can bring research forward by doing things that were not possible before.
Okay, but excuse me to interrupt you here.
Yeah.
So what you're showing here, it's technically a part of the science process where you have to develop your own tool, and
Yeah.
technically you're part of the R&D process.
Mhm.
But what is the openness in that? I mean,
Yeah.
you created that, but it's not there. What is the point of making that open? That would be my main question. Let's say that I'm another visual neuroscientist, and I need to adapt that to, I don't know, here, for example, that's for zebrafish.
Yeah.
Apparently, according to you, I can modulate it to whatever I can, but what is the point of making it open? What will be the point of our colleague in vision research to invest time reproducing it?
So what we did, what we tried to do was to put the documentation online in a way that everybody can reproduce it. So there is the paper that I already described, and this was published in eLife. Big shout out to the eLife guys, because right now it's a super cool way to publish papers there. And we published all the step by step on how to build it, what parts are needed. There is a view of materials, how you can calibrate it, how you can make sure that it's really, really properly working. And so in the lab, we're using this for zebrafish, but as well for cheek retinas, right? And so this already shows one of the points is that initially we started with zebrafish, and then already got picked up in the lab for cheek retinas. We have a different spectra, wavelength spectra for the avian cones, right? And the point is that as we publish the paper, we're hoping that the community is going to pick this up and derive it to other species. It's already been used for mice in Tübingen, where it actually initially started its development. And we're hoping as more people contact us and get in touch, we can help them and guide them through, okay, maybe let's say I want to do this super cool experiment with the mantis shrimp, which also has like crazy spectra for their vision system. And we could help them with 6 different LEDs to stimulate, like this is of course like me talking hypothetical at this moment, but this is what we hope for, that we set like a landmark and a starting point for the community to build upon. And so this brings another point of open source, which is we took the initial effort of developing this. Hopefully somebody's going to come up and profit from this in the sense that they will derive it, make it better, and share it back to the community. So they profited because they didn't need to start from zero, and we profited because whatever they developed better and new, we didn't need to develop ourselves. So we get 2 for the price of 1, so to say.
So if I transfer what you're saying, it means that wherever and whenever you have a lab that is developing a new tool that fits their own research, most of the time it will appear in the methods, in the papers that says, okay, we develop whatever tool to accomplish whatever study. But the thing is that most of the time they don't share the blueprint or the approach or the successes and failures in terms of developing the equipment.
Yeah.
So what I'm claiming here is that on top of just sharing our data or results, we should also share our methodology protocol to be actually being able to reproduce it and speed up the innovation cycle that we're encouraging here.
Yeah. So sorry to interrupt you, but I think this is very fitting with this. I think it's a historical reason why our methods got shorter and shorter, right? And this is like a whole different discussion, and I don't want to go into details about that. But what we know is that big impact journals have very little space for methods, and you have then this online method, supplementary material, and so on, which kind of encourage this practice of putting very, very short methods and very short descriptions, which is detrimental. And so luckily for us, what is happening is that now technology is evolving to a point where you have more space and internet bandwidth and so on. So you can actually share things by yourself in a repository and be super detailed. And so you can have text, you can have photos, you can have videos, you can have really a step-by-step guide. And even if the high impact journal that you're sending this to doesn't have the space for that, you can still share your repository as a link, and then people can go there and say, look, this is how we did it. This is the step-by-step. and you can like really follow on it.
Fully agree.
And yeah,
One little flaw in there. I mean, I read a lot of papers and I try to reproduce most of them. You and I will review some open source paper, and most of the time we fail to reproduce it because
right.
sometimes a code will be missing, or they didn't forget, or they upload the first draft and didn't correct it. The thing is that, to put simply, claiming that something is open source
Yeah,
doesn't make it open source. How can you compel people to actually follow a guideline
yeah,
to actually, because there's plenty of repositories. I
yeah.
can't even keep track with the amount of repositories, but they're not all words the same. I would,
Absolutely. So this is the beauty and the curse, a little bit of open source, the diversity of it, because you have people that are building tools all over the world and they have their preferred platforms. You have GitHub, you have Instructables, you have Hackaday, and so on. And so to cover this problem, this very nice group of people got together for a number of years now, got together and made the Open Source Hardware Association, as you're showing. And what they developed was a certification program for open source hardware. And this is a very low entry certification process. I mean, low barrier entry certification process, where you basically put all your things in a repository. And because they have a definition online, they're already telling you what they expect. And they have a definition of what is open source hardware. And so they tell you what do they expect in terms of what files are you sharing for people to be able to reproduce your design. And so once you go in there and you say, okay, I need to share, these are just examples, share files that are editable, right? So this would be similar to, instead of sharing a PDF or something, you'd share the Word doc of that, right? Of course, you can modify a PDF and actually translate it back into something editable, but that's hard work. So what you want to do is share the editable file from the get-go. And so, not going on that much longer, but the point is, if journals and academia in general would, for instance, pick up the Open Source Hardware Association certification process, we would have a very nice starting point, a very nice standard for open source hardware in academia, where if the hardware that is being described in the paper is certified, I already know what to expect, right? I know that the files are going to be properly there and so on, because the certification process of the Open Source Hardware Association makes sure that all of the files are there and are present and are in a certain format. And the benefit for researchers here would be there are already many companies and many people who are building their own tools outside of academia, certifying their projects. And so this would get academia closer to, let's say, the general public and to companies and to people who are interested in hardware, but not necessarily in this very small space that is academia. And then again, this is again the idea of like, this is public money. It needs to be brought back to the public. This would be a nice way of actually getting attention that with public money, we're building these cool tools, that then the public could reproduce them.
and that can benefit the public. Actually,
Yeah.
we have recent examples of good practice in open hardware. We have the
Yeah.
kind of ventilators that were developed during the COVID
Yeah.
time.
So this is actually a fantastic example. Unfortunately, during the pandemic, we've learned a lot of things that showed us that our supply chains are not super reliable the way we like to think they are. So we had this problem. The pandemic started in China, a lot of lockdowns there, a lot of things got delayed. There was a shortage of personal protection equipment and so on. And so what a lot of people did was actually started building these things locally. And here you're seeing a paper that we published in the beginning of 2020. This was together with Tom Baden, Lucia Prieto Godino, and Jenny Molloy. This is again trying to make, and this was very fastly like we had to write it in a very short amount of time. At that moment in time during the pandemic, there were all these groups popping up building things as complex as ventilators, right? So these are life-saving machines that are really needed and really shortage in a lot of places and really expensive. And so all of these groups started building these ventilators, and some of them are actually already in use or in testing in hospitals. And the benefit of them is that, I mean, you can see here that you have all of these different models, but like I think the biggest benefit of them is that because they are showing how to build them and they're open source, you can actually see the list of materials and easily source them locally, because it's much easier to get locally small components and small electronic components that might already be stocked in certain shops even before the pandemic started than it is to get a complete built ventilator shipped from somewhere across the world. And so this again goes in line with, and this going back to the idea of equipment in academia. If you think about, I'm originally, as you mentioned, like I did my bachelor's in Brazil, this is where I'm from. And I remember back then that even when you had the grant money to buy something, it would get stopped in customs, and then there was a big delay, and then the prices for custom taxes would be super high, and then the equipment would be more expensive. And then when you finally got it, it worked for a number of years, but then if it eventually broke or if you needed an upgrade, you wouldn't have um, a
Supplier.
local customer service to fix it. And so you would have either to ship it all the way back, and then super expensive, a lot of time, same
Mhm.
problem with customs and so on, or you would have to put it to the side and buy a new one.
Yeah, and just throw it away while it can be fixed for.
What? Yeah, yeah, exactly.
It's a
And
common problem.
so, and it's a common problem, and it's a common problem for, if you think about electronics in the world in general, right? How many times have we seen like a broken phone with a broken screen, and then you toss it and you buy a new one?
Mm.
And the reason for this is that these things are normally made hard to repair and so on. And luckily for us, and this is, I think, tangentially related to this, is that Europe has just passed this right to repair law, where um, companies supplying electronics and making electro-electronics for home, they need to make um, tools or equipment that is now easy to repair, or that the parts, the spare parts to repair them, are available for at least 10 years. And so this helps with electronic waste, also helps with being able to not throw away a big, gigantic tool just because like a little tiny resistor or a little fuse broke inside it,
Oh.
and so on. And again, it's much faster to replace a part inside than it is to get a new one.
So you fight companies against program obsolescence,
Yeah,
and this
exactly.
system can be applied to scientific equipment.
Equipment as well. In principle, you should be able to apply that to scientific equipment as well.
I mean, I completely agree with you. I mean, what we can say now is that with the democratization of electronics, the expiration of most patents, the fact that we have access to multiple repository online, technically we can say is that the innovation cycle just go back to researchers. But the thing is that it's still underappreciated. So how do you encourage our peers, fellow researchers, how do you implement in our daily research this kind of practice?
I think it's always easier to convince people or to show people
Mhm.
the benefit of something if you can solve a problem, or if they can solve a problem that they have.
But
So what I normally suggest is that if somebody is interested in starting to learn how to build tools and they see the benefit, they just don't know where to start, right? I tell them, look, find a small problem that you have. There are all these tutorials online, there are all these electronic kits. You can buy a little kit for 50 bucks and you can put things together, let's say a temperature sensor, that when you put it together with other electronics, it's going to send you a message, an SMS or an email, whenever the temperature in a room goes below a certain value or above.
Mhm.
And so with this, you could create a, let's say, a protection system for lasers in a two-photon microscope. If your room temperature goes above a certain level, you get a notification saying, look, that room is above a certain level. You might as well go there and turn off the laser, otherwise it's going to damage things. And so by building this little device for, let's say, 10 bucks, you're going to save a very expensive laser from being damaged.
Yeah, but the time I will, let's say I have a PhD student, is naive about most of the things, the time he will spend trying to understand how that works, would that be worth it instead of just buying a 50 thermosensor?
Um, yeah, so I mean, I think it is worth it because when you learn these things, you're not just learning how to put a temperature sensor together.
Mm.
And so, of course, it needs to be weighed, how much time you need to build these things and so on. But my point here is biologists will need more and more to know how to program. And a lot of what we do with hardware and electronics is based, or it has a big programming component. So learning these, you could use as a tool to learn how to program, and then these you're going to use for the rest of your life. Data analysis, automation of certain pipelines, and so on and so on.
So you start low, but you implement it more and more along user research, and then you can innovate because you know it's accessible.
It's an incremental process, right? I studied biology and I didn't start building visual stimulators. I started with little tools and little things that then got, because then you learn these things and you get packaged, then you can improve and do things differently. So it's not really that much time consuming to start. You need maybe like an hour a day with a little electronics kit to get started. But another way that this would be entirely very much helped is if there was top-down investment, right? If universities and institutes and departments would say, okay, we need to come up with, let's say, an open science module for our PhD students or for grad students, where you teach them all of these little aspects of open science, open access, open data, reproducibility, how do you put code together and share it with others, best practices in keeping your data for a long time, and so on and so on. Electronics and all of these things. These will make them better researchers. This will make the results of research better and more replicable.
Yeah, it's definitely good. It's basic good scientific practice.
And yeah, I mean, absolutely. And there is a very big return of investment here, because as you are more independent from needing to get something that it's already made, research can be faster and you can test different things and you can go in different directions. And the other thing is that these are normally life skills, in the sense of, if you know how to program Python, there is a huge market for Python programmers outside of academia. And as we know, we are putting out more PhDs, or people are graduating with PhDs in a higher pace than we have permanent positions in universities to absorb them. So we know that people are going to leave academia anyways. Not everybody's going to stay. And so if they have skills that are desirable by the market, then they are better off as well.
Yeah, right. But back to academia, so you consider that maybe it's a duty of universities to propose or to suggest some kind of more technical courses, interdisciplinary modules?
Yeah, I mean, absolutely. So in a way, the idea of a university campus was that made that you would be the biology close to the engineering department, and then it would be like a short walk so that you could talk to an engineer and actually build something together to do your experiments.
But that's never
right. Unfortunately not. But this could be revisited maybe. And the other point is that, of course, I don't think necessarily you need the universities to take care of this. Even students could start with little clubs, as we had here in Sussex, where we had the coding club and all these workshops. But again, like a big entry barrier would be lowered if there was a space from from top to bottom to say, look, this is a space where you can come and create and so on. And we do know of places that are starting with this. So you do have interdisciplinary labs. There are places in Paris that are like this. Like, this is something that we're trying to create here in Sussex as well, where you have a lab and a space for people to come and learn things as part of their studies. And this could be seen. Sorry, and this could be seen as a interdisciplinary, let's say, PhD. Right, part of your PhD is actually developing the tools that are going to guide the question that you had. And so there is a component of engineering. You could partner up with an engineering lab, and then part of it is actually collecting the data. And so you could make this to fit quite nicely with the PhD track in a way.
Yeah, I agree. But I mean, what I meant to say is you cannot invest time on something that you ignore exists. So at first you have to make clear to, let's say, those new scientists, those PhDs, those masters, that, I mean, how many times do we see people following old laboratory practice that date from 2 decades ago? You cannot improve on a protocol where you don't know that you need to improve on it, and the solution is actually a key. What I mean by that is, right now, you start in a new position at the University of Sussex, where you develop different kind of tools. And actually, right now, you're trying to create a new lab, an open science lab. Do you want to share with us, I mean, are you try to alleviate locally. I mean, I guess you'll be the best example to show how you convince other people that we need to invest in time and effort.
Right. I mean, this is so far still like a moonshot project, right? Because I'm still like trying to put things together and know exactly how it's going to work. But the idea is what I meant. So we need to create a space where there will be knowledge and expertise for people to learn about all these different aspects of open science, including hardware. And so, of course, people don't know what they don't know. But if you come to a place where there is, when you first come for a PhD, there is every semester, let's say, a course that is maybe mandatory or not, but there is a course dedicated to telling people, look, this is what we can do nowadays with the open source technologies that are available. This definitely then opens up the mind to say, okay, I can actually do this. And there is a supporting space here that is going to guide me through it, which is already what's happening here in Sussex. Because there are already a lot of projects that are getting started where we're building new things for the labs that are things that are not, that were either very expensive or things that were not existent before.
Yeah, fully agree. And like I said at the beginning of the talk, you created some kind of repository of repositories.
Yeah, so Open Neuroscience, you mean?
Yeah.
Yeah, so Open Neuroscience was something that started many years ago, and it was a way for me to keep track of all the open source projects that are there. But I think we have somebody here especially to talk about this who has been collaborating with Open Neuroscience. Hi, Ceci.
Hi, everyone. How are you? Thank you for having me. Yes, I've been collaborating for over a year now. I'm Cecilia Herbert. I'm a PhD student at the University of Buenos Aires in Argentina. And please excuse the noise. There's some construction going on here. So I hope you can hear me well. Let me just share my slides. Okay, that should do it. Great. So today I wanted to tell you a bit about Open Neuroscience. This is an initiative that curates open source projects related to neuroscience on openneuroscience.com. Projects are not only hardware, like we were discussing just now, but also software, data, and educational resources, and others. The database is user-driven by the community. So while we are on the team are on the lookout for projects all the time, anyone can contribute to the site. And of course, you can browse all of these projects freely. What we do is basically we check each submission to make sure it is at least vaguely related to neuroscience, but more importantly, that it really is open, meaning that the source is readily available, as Andrea was just explaining. Then we publish it on the site and announce it on Twitter. So at this point, especially after the talk we just had, you're probably thinking, okay, this is great, it's so relevant, and it can be so useful. So how can I help? So let me just make an aside here. I was telling you, yes.
Ceci, sorry to interrupt you, but I think we can see your author's note, your presenter's note. Yeah, that's fine. That's absolutely fine.
Okay. Well, that was my script for today. What I was saying is that a year ago, I was maybe sitting where you are just now, right? Listening to Andrea talk and saying, this is great, I want to jump in. So what you can do to help Open Neuroscience, you can, first of all, submit a project if you have one, or if you know of any project that fit the bill. This is our upload form. It only takes a few minutes. You can also spread the word about the site as well as use it. You can follow us on Twitter. That's where I just said that we announce all the projects. And you can collaborate over on GitHub by solving issues. That there are always some issues, right? Another thing you can do is contact us over at openneuroscience@gmail.com if you would like to collaborate further and maybe work on some organizational aspects. And you can also give a talk. So give or attend a talk. This is our new seminar series that starts this week. It's going to be every Friday at 15 GMT. on the Worldwide Science platform. So we're both on the Neuro track and on the newly opened open source track of the seminars over at Worldwide. And please join us. This is the schedule for April. We're starting this Friday, as I said, with Anton and Pavel about giving a talk about a platform for automation of cell biology experiments. And we have a few other speakers lined up for the next few months, and you might be the next one. So this is the form to schedule the talks, and we hope to see you there. I really want to apologize about the noise. They just started when I had to speak. Thank you so much.
All right, thanks for that, Ceci. You will find all the necessary link in the description of this video. So you will find all that we shared, all the necessary links, and also links for open neuroscience repositories. And yeah, of course, we will share in our networks and in our programs upcoming talks. So I hope to see most of you during those talks, let's say.
Yes, please.
So do we have questions? I have one stupid question.
Mm-hmm. You're muted.
Hey, Andre, my boss won't buy a printer. What can I do?
Well, that's a tough one. A lot of the times I say, and please don't quote me. I mean, this is going to be recorded, so people are going to quote me on this. Sometimes it's better to ask for forgiveness than to ask for permission. And printers nowadays are at the rate of $200 on eBay. And they're actually not shitty printers. They're actually okay-ish printers. You can actually print stuff with them. And at this level of cost, you could get together with other people and everybody pitches in a little bit and buy a printer for the department. And the benefit of it is that the return on the investment of the printer comes really after you print it for as little as 5 hours, right? Because you can print things that are way more expensive to buy than it is to print them. And so really quickly you can get your money's worth for the printer and the filaments you bought. And there are papers actually showing this return of investment into investing on open source hardware and in financing open source hardware. And so I think all of these links are in the description of the video. And so people can take a look at them. But yeah, so my recommendation would be maybe get together with friends, either buy a printer or you can find a local makerspace.
And you have a lot of fab labs around you.
There are a lot of fab labs around and makerspaces and in a lot of places of the world. And so you can actually go there, print things, get help, meet a community, and then you can bring those to the lab to actually try to make the point. Look, we printed all of this. This is much better and much faster than what we had. Therefore, here's the evidence to buy a printer.
We have Garrett from Newcastle with us.
Mm-hmm.
So he asks, do you know a source site that is mainly dedicated for use of open hardware in higher education teaching, ideally with neuroscience-related hardware, for example, EMG, ECG, which can dismantle, there's a B missing, which can be dismantled after the practicals?
Yeah, absolutely. So, I mean, Open Neuroscience has a lot of educational projects. But I think for what he mentions, Backyard Brains would be a very good candidate. They are actually a company building neuroscience tools for education, and all of their tools are open source. And so you have an EMG amplifier, which is this big, and it's powered by batteries, and they have a lot of cool experiments and tutorials online. And so people can, build stuff directly, and they don't need to disassemble them because they're small, and you can put them in a backpack and then take them home, basically.
Actually, Backyard Brain is a very good example, and I can only encourage to see a Greg Gage talk on TED. He made a couple of talks, and he's mostly focused on what is the opposite of higher education, lower education?
High school, I would say. So not education in universities.
But you can find all kinds of education tools that can be used at different levels. So that would be a good start, yes.
Yeah, although we also use their tools in training courses for people who had never had experience with electrophysiology. And so you can actually do their experiments in a higher education setting as well.
I just want to precise that what you refer to is trend in Africa. So when you organize a workshop in Africa, those kind of tools are useful for people without regular resources.
Yeah, no, but I mean, this you could also do anywhere, right? Because let's think about the bachelor's here in neuroscience. You can take people into the labs. I mean, normally you would take people into the labs and show them the big behavioral rig and so on, but then they don't get to actually like do the measurements and put things and so on. So you could build a little electrophysiology rig, let's say maybe 10 of them, have people in groups of 3 people and actually get them to record the data and analyze and do like little experiments with electrophysiological data. So you don't really need to be just in Africa. I think this is a very important point. Like this stuff is not just where you don't have access, but really, can we change the way we teach things by having more hands-on because we have access to equipment or more equipment?
I agree. That's something we haven't talked about, but the philosophy behind open source hardware actually allows universities, labs in lower income countries to actually have an equal access to science and protocol, and they can actually produce a same level of data, the same.
Absolutely. So there is a democratization and an increase in accessibility for research equipment. Yeah.
Well, thank you for that. I don't see any other questions. I guess we covered most of it. So I can only recommend our audience to keep track on the Open Neuroscience series that will start this Friday. And I guess you will definitely find an open source project that will fit your need or will find of interest. So take a look at the website, take a look at the upcoming series. We will advertise it, and we hope to see you there.
Yes, please.
A final word?
Well, thank you everybody for their time. Thank you for everybody who's been collaborating and picking up on this until not long ago seemed crazy and hippie ideas. And I think it's important to say that this is gaining a lot of momentum. So there are more and more open source hardware coming out. There are 2 dedicated journals now for open source hardware. There is Hardware X and the Journal of Open Hardware. Plus already also does a lot of open hardware publications. And there is a wonderful community online called the GOSH community where people should have a look. I don't know if we're going to have links on the description of the...
I will add it.
Yeah, okay. And so the GOSH community is really a global community talking about open science hardware. And the last thing that I would like to say is together with Julieta Arancio and Alex Cuchera, we're creating a mentoring program. We're not going to be mentoring people, but we are organizing a 14-week online course on best practices of open hardware, where there are going to be mentors who are specialists in the field of open source hardware to guide people through what are the best practices in open hardware, how to foster a community, and what are the best ways to build tools and to interact with this community. So we're right now revamping our curriculum, but we hope to launch this soon. So please have a look at the website, which Maxime is showing now, which is just openhardware.space. I think we're going to have a link on the description as well.
We have.
And yeah. And so this is a wonderful place for starting projects, for mature projects, for all types of open source hardware projects.
All right.
Thank you.
Thanks, everyone. See you soon.
Thank you.